In this video, we will start to talk about a new version of linear regression that's more powerful, one that works with multiple variables or with multiple features. Here's what I mean. In the original version of linear regression that we developed, we had a single feature x, the size of the house, and we wanted to use that to predict y, the price of the house, and this was our form of our hypothesis. But now imagine what if we had not only the size of the house as a feature or as a variable with which to try to predict the price, but that we also knew the number of bedrooms, the number of houses, and the age of the home in years. It seems like this would give us a lot more information with which to predict the price. To introduce a little bit of notation, and we sort of started to talk about this earlier, I'm going to use the variables x subscript 1, x subscript 2, and so on to denote my, in this case, 4 features, and I'm going to continue to use y to denote the variable, the output variable price that we're trying to predict. Let's introduce a little bit more notation. Now that we have 4 features, I'm going to use lowercase n to denote the number of features. So in this example, we have n equals 4 because we have 1, 2, 3, 4 features, and n is different from our earlier notation where we were using m to denote the number of examples. So if you have 47 rows, m is the number of rows in this table or the number of training examples. So I'm also going to use x superscript I to denote the input features of the ith training example. As a concrete example, let's say x2 is going to be a vector of the features for my second training example, and so x2 here is going to be a vector 1, 4, 1, 6, 3, 2, 40, since those are my 4 features that I have to try to predict the price of the second house. So in this notation, the superscript, the superscript 2 here, that's an index into my training set, right? This is not x to the power of 2. Instead, this is an index that says, look at the second row of this table. This refers to my second training example. With this notation, x2 is a 4-dimensional vector. In fact, more generally, this is an n-dimensional feature vector. With this notation, x2 is now a vector, and so I'm going to use also xi subscript j to denote the value of the j of feature number j in the ith training example. So concretely, x2 subscript 3, let's say, would refer to feature number 3 in this vector, which is equal to 2. Right? And that was a 3 over there, just to fix my handwriting. So x2 subscript 3 is going to be equal to 2. Now that we have multiple features, let's talk about what the form of our hypothesis should be. Previously, this was the form of our hypothesis where x was our single feature. But now that we have multiple features, we aren't going to use this simple representation anymore. Instead, our form of the hypothesis in linear regression is going to be this. It's going to be theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 4 x4. And if we have n features, then rather than summing up over our 4 features, we would have a sum over our n features. Concretely, for a particular setting of our parameters, we may have h of x equals 80 plus 0.1 x1 plus 0.01 x2 plus 3x3 minus 2 x4. This would be one example of a hypothesis. And remember, a hypothesis is trying to predict the price of the house in thousands of dollars. This is saying that the base price of a house is maybe 80,000 plus another 0.1. So that's an extra $100 per square feet. Plus the price goes up a little bit for each additional floor that the house has. So x2 was number of floors. And it goes up further for each additional bedroom the house has, because x3 was the number of bedrooms, and the price goes down a little bit with each additional age of the house, with each additional year of the age of the house. Here's the form of our hypothesis rewritten on this slide, and what I'm going to do is introduce a little bit of notation to simplify this equation. For convenience of notation, let me define x subscript 0 to be equal to 1. Concretely, this means that for every example I have a feature vector x superscript I, and x superscript I subscript 0 is going to be equal to 1. You can think of this as defining an additional 0 feature. So whereas previously I had n features, features x1, x2 through xn, I'm now defining an additional sort of 0 feature vector that always takes on the value of 1. So now my feature vector x becomes this n plus 1 dimensional vector that is 0 indexed. So this is now a n plus 1 dimensional feature vector, but I'm going to index it from 0. And I'm also going to think of my parameters as a vector. So my parameters here, right, that would be this theta 0, theta 1, theta 2, and so on up to theta n. I'm going to gather them up into a parameter vector written theta 0, theta 1, theta 2, and so on, down to theta n. This is another 0 index vector, so if index starting from 0, that is another n plus 1 dimensional vector. So my hypothesis can now be written theta 0 x0 plus theta 1 x1 plus dot 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 up to theta n xn. And this equation is the same as this one on top because, x0 is equal to 1. And the neat thing is I can now take this form of the hypothesis and write this as theta transpose x. Depending on how familiar you are with inner products of vectors, if you write out what theta transpose x is, what theta transpose x is this theta 0, theta 1 up to theta n. So this thing here is theta transpose, and this is actually a n plus 1 by 1 matrix. It's also called a row vector. And we take that and multiply it with the vector x, which is x0, x1, and so on down to xn. And so the inner product that is theta transpose x is just equal to this. This gives us a convenient way to write the form of the hypothesis as just the inner product between our parameter vector theta and our feature vector x, and it is this little bit of notation, this little extra bit of notational convention that let us write this in this compact form. So that's the form of our hypothesis when we have multiple features. And just to give this another name, this is also called multivariate linear regression. And the term multivariate is just maybe a fancy term for saying that we have multiple features or multiple variables with which to try to predict the value y.